Welcome to Acids and Bases Part 2. In this portion of the video tutorial series, we're going to focus on nomenclature of acids in particular. Because you know how to name organic acids, but we need to learn how to name inorganic acids. So we'll review and build on that understanding. Let's get started. Alrighty. So particularly for inorganic acids, we will symbolize them HXA-. So inorganic, right, this part's telling us not carbon-based. All right. And so when these acids are added to water, they release the hydrogen ions and an anion. And so when we're talking about acids, we're really focusing on this part here. Right? But all acids have this in common. This is what makes, right? So all acids have H+. So if we're trying to distinguish between the acids, this is what they have in common. So that's not going to help us. What's unique to each acid is the anion that's also released. So when we're naming acids, it is the anion that is going to drive the acid name. And if we look at our anions, we'll note that there were only 3 different suffixes for all of those anions that we've learned. So we've learned anions where the suffix is "ide," "ate," or "ite." So anything in front of this suffix is considered the root or the stem. So when we're naming the stem or the root, this is the part that is unique to each acid. So that's the part that changes with each acid name. The rest of the acid name is determined from the suffix. So when we have an acid that the anion name ends in "ide," that acid name will always be hydrostemic acid. When we have anions that end in "ate," it's an ic acid. And when we have anions that end in "ite," it's a us acid. So let me do a couple examples here to help you understand. So for example, if we have HBr, we recognize that there's our anion, right? Bromide. All right, so everything in front of "ide" is the stem. So when we go to draw or write this name, because of the "ide," we know it begins hydro. Then we would bring in our stem, brom. And then we're back to the generic part of the name, right? So HBr is hydrobromic acid. Let's do one more to make sure we get this. Let's try HCN. So here we recognize cyanide. Everything in front of "ide" is considered the root or the stem. Because the anion ends in "ide," we know that we're going to have hydroic acid. Simply from the "ide" suffix, we get all of that. The only thing that changes is the stem, the part that's unique to hydrocyanic acid. Okay, so it's going to be the same strategy for the other acids. We'll just simply change the format, right? So 8 becomes ic. So if we look at HNO3, we recognize our nitrate ion. So everything in front of 8 is the stem or the root. So the 8 part tells us ic acid. and then the stem, so this would be nitric acid. Another very important acid, especially in biological systems, H2CO3, we recognize the carbonate. So just like before, everything in front of 8 is the stem or the root. The 8 part tells us the ic acid part of the name. So, and then we bring in the stem. So H2CO3 is carbonic acid. Alrighty. And fortunately, there's only one last suffix for anions, and that's the ite. So whenever we have ite as a suffix, we will use us acid. So some examples here, we have HNO2, so that has nitrite. So everything in front of the ite is the stem or the root. So that would be, there's our stem or root. And then the ite part tells us we write us acid. One last example here to make sure everybody feels comfortable. Oops, no, we just want it like that. HClO. So that is, right, hypochlorite. So in this case, the stem is huge, right? The stem actually includes a prefix, so everything in front of ite is part of the stem. So this would be hypochlor. There's our stem or our root. And then the ite part tells us that we change the suffix to hypochlorous acid. Alrighty. Now, there are only 2 types of acids that have a variation or an exception. I'll use these 2 acids as examples, right? So our sulfur acids, when we have a sulfur acid, we add UR to the stem. All right, so I'll put that in a red box. Okay, so if we follow, right, the rule for 8, so if we look here, SO4 2-, we would say that's sulfate. All right, so here's the original stem. So the 8 part tells us, right, that we want an ic acid, so the 8. But then we are going to write our root, but we add the UR to it. So it becomes sulfuric acid. In a similar fashion, when we have phosphorus-based acids, we're going to add an OR to the stem. All right, so we'll put that in red as well. So just like before, it's PO4 3-, that's phosphate. All right, so here, everything in front of 8 is the original stem. So if we wanted to name this acid here, we begin with the phos, and it stops at the H. And now we add the OR, and then the 8 part tells us ic acid. So in naming sulfur-based acids, we add a UR to the stem, and for phosphorus-based acids, we add a OR to the stem. Okay, so now we have a good introduction to inorganic acids. Let's have a brief review of organic acids. So because we're focusing just on organic acids, it simplifies the nomenclature rules a bit, right? So we're always going to find the longest continuous carbon chain that has the functional group, and the carboxylic acid will always get It's at the end of the chain, so we don't have to tell anybody. Everybody knows it has to be carbon 1. And so if we looked here, we have a 5-carbon chain. So from the homologous series, we would call that pentane. But then we see that we have a carboxylic acid, so we replace the ane with anoic acid. So now if we rewrite this, and then we have one last bit here. We have a branch. So there's a methyl group coming off of carbon 3. So to name this compound, 3-methyl pentanoic acid. All right, there we go. Okay, there's one carboxylic acid that we're going to encounter quite a bit. Its structure is right here, and you should all be able to name that, right? The name of this carboxylic acid is acetic acid. And that's the acid present in vinegar. Okay, so let's have a quick review of our IUPAC nomenclature for organic acids. So go ahead and take a minute now to name these, and then we can compare answers. Alrighty, so we find our longest continuous carbon chain, and then we notice that we have 2 branches, ethyl and methyl. Alright, so we number the chain to give the carboxylic acid the lowest possible number, and we always cite our substituents alphabetically. So now we can go ahead and name this acid. 3-ethyl, 4-methyl, right? Homologous series 6 would be hex, and then hexanoic acid. There we go. And then as we transition to biological molecules, we think we already know, or we will know, amino acids are important biological molecules. And so we want to recognize that the carboxylic acid is the higher priority. So when we look here, the amine is considered a branch. So we call it an amino group. So just think about amino acids. So just the name as we learn it tells us and reminds us. And then we put we have a methyl group here. Okay, so if we wanted to give the IUPAC name, right, we cite the substituents alphabetically. So this would be 2-amino, 3-methyl, and then, right, bute, 4-carbon chain, butanoic acid. When we get to the chapter on amino acids, we will learn that this amino acid is valine. So I won't ever expect you to memorize all of the amino acids, but just a bit of a segue as we get ready to study biochemistry. Okay, now that we have reviewed and introduced different aspects of acid nomenclature, we have a review page here. So this would be a good time to pause the video and answer, fill in this table as best you can, and then we can compare answers. Alrighty. So when we look at this first compound, iron, we recognize iron is variable charge, right? So we don't know, is this iron 2+ or iron 3+? We don't know. How do we answer that? We look at the anion. So when we look at this anion, we see chloride, and there's 3 of them. So there is a net -3 charge. So the anion tells us this compound is neutral, so it's iron 3. Remember that when we're naming ionic compounds, it's all about the charge. So iron 3 tells us it's iron plus 3 chloride. And since in this molecule, it's not a proton donor, and it doesn't accept hydroxide, and so we would describe it as neutral. Back in the good old days before we knew about acid-base chemistry. Now we have an organic acid. So we find the longest continuous carbon chain. Note any branches. So 3-methyl, and then a 5-carbon, right? That would be pent. And the carboxylic acid tells us anoic acid. And acid, base, or neutral, this one's pretty easy. If acid's in the name, we know it's an acid. Here, we know barium. We know barium is an alkali earth metal. It's always +2, so we don't have to tell anybody, because anybody that's reading this formula also knows that barium is always +2. And once again, we have a neutral, right? So an ionic compound, that's a neutral salt. Alrighty, here we have our buddy carbonate. So this has carbon, but we lump it into the inorganic nomenclature, right? So focusing on the 8, the 8 tells us that we're going to have ic acid, and everything in front of the 8 is the stem. So this is our carbonic acid, and once again, if acid's in the name, we know it's an acidic compound. Here we have another ionic compound. However, in this case, it's an ionic compound that will release hydroxide ions. So in this case, we refer to it as a base. So in some contexts, you could think of acids and bases as a special type of ionic compound related to the hydroxide and hydrogen ions. So we would name this just like we would any ionic compound. So potassium hydroxide. Okay. Now, it's really important that we keep this distinction. Here, we have our cation and our anion. So this is an ionic compound, and because of its ionic nature, we describe it as a base. However, here, notice this compound. This compound has 4 carbons, let's see, 10 hydrogens, and an oxygen, right? All nonmetals. This is a covalent compound. So there is still a hydroxyl group, but this is an alcohol. And alcohols are neutral. So when we see the hydroxyl group, hydroxide versus alcohol, it's important to make that distinction. So when we're naming this compound, right, we want to give the alcohol group the lowest possible number, and we have to let everybody know where it's at. So 2, it's a 4-carbon chain, and then we let everybody know there's an alcohol present. And last but not least, here's a condensed formula. We see we have a 3-carbon chain with an amine group coming off of the 2nd carbon. Now here, the amine is the only functional group present, so it gets to have the suffix position. So we let everybody know where the amine is, and then we give our homologous series prop, a 3-carbon chain, and so an amine, there's our suffix. And we remember that amines are bases. They're weak bases, but they're still bases. Alrighty, so now we just have one page to wrap up and tie this together with our previous tutorial on introducing acid-base reactions. So, the amazing thing to me is that there are only 6 strong acids. Of those 6 strong acids, you want to memorize these 5. All right, so then we can practice our acid nomenclature rules by looking at the anion. Right, so we have chloride or bromide or iodide, nitrate, or sulfate. So then, based off of these anion names, we can apply our rules of inorganic nomenclature, right? Distinguishing, looking at each ion name in terms of a stem or a root and a suffix. So for the ides, right, these will all be the same. They're all going to start with hydro. And that hydro comes from the fact that they end in ide. They each have a unique stem, hydrochlor, hydrobro, or hydroiode. Okay. And then the ide tells us they each end in ic acid. Okay, I put pretty big spaces there. I'm not sure why. Okay, now we get to the 8s, right? So with the 8s, it's ic acid. And this last one, you don't need to memorize, but it's the only other strong acid. So, and it's also an 8, right? So when we have ides, hydroic acid. When we have 8s, ic acid. And then we simply bring in the stem. So this would be nitric acid. Remember, with the sulfur-based acids, we add that extra UR. And then for this last one, perchloric acid. Okay, so it's a good idea to memorize these 5 because remember, strong acids react completely, so we will show the complete reaction arrow as we've seen here. So recognizing we have our amine, which is a weak base. And then here we have our strong acid. So for a reaction to go completely, we just need the acid or the base to be strong. As long as one of them is strong, we get the complete reaction. And in this case, we form the ammonium salt. And we'll study this chemistry a lot more because it creates water solubility, and we'll learn that amines are very biologically active. A lot of drugs and medicines are amines, and so we will explore this chemistry quite a bit in the future. So then this is a big deal, right? All other acids are weak acids. So if it's not one of these 6, then it is a weak acid. Right? And so when it's a weak acid, they do not react completely, right? So it's equilibrium. And so, but once again, we can recognize here is our weak base. And then our carboxylic acids are weak acids. And so we will get both the forward and the reverse reaction occurring simultaneously. Okay, so that concludes our tutorial on acids and bases, focusing on acid nomenclature. Please take the time now to name a few more acids to reinforce your understanding.